Hello, everyone. We are going to start chapter 4 today. We ended the last chapter with a discussion of the fact that we are transitioning to the second part of calculus, that of integral calculus, which we began with a discussion of how to find antiderivatives. This particular section that we're going to do in chapter 4 will seem a little bit off topic, but you'll see as the chapter goes on that it is right in the middle of integral calculus. So we're going to talk today about area and distance and how to find those. So let's get started. First of all, we know the following. We know how to find the following areas. How to find the areas of shapes such as the following. We know how to find the area of a rectangle that has a certain length, a certain width. I know that the area is equal to the length times the width. So I have a specific formula that allows me to calculate that. Very similarly, if I'm given, say, a triangle, such as this, with a certain height, call that h, and say the length of the base is b. If I'm given that, then I have a formula that allows me to calculate the area of that. A, I would find by taking half of the base times the height, which actually that comes from knowing the area of the triangle or the rectangle, excuse me, that triangle is contained in. If I take half of the area of this rectangle, which I'm showing in red, then I get the area of the enclosed triangle. So that leads back to area of a rectangle. I can find the area of, say, this shape, which is a polygon. It's not a regular polygon, but it is a polygon. I can find the area of that because I can divide this polygon up into triangles. And I have a formula that allows me to find the area of each of those triangles, which I got from the formula for finding a rectangle. So if I call this area 1, call this area 2, call this area 3, call this area 4, then the total area of this figure is the sum of all those areas. Okay. So these are all polygonal shapes. They're all figures with straight sides. And I have specific formulas that you've probably known for a very long time in your mathematical history, how to find the area of such shapes. But not all shapes are that simple. Let's consider the following region or shape. A region would be an area enclosed by curves. I'm going to draw a coordinate plane here. And let's say I have this function, f of x is equal to x squared is equal to x squared. Let's say this point here is 864. What if I want to try to find the area underneath that curve between f of x is equal to x squared and the x-axis? So what if I want to find this area here? Well, due to the fact that this is a curved line, it is not a straight line, I don't have a formula that allows me to do that. So I'll go ahead and write that down. I have no formula that allows me to find the shaded region. That allows me to find the shaded region, the area of the shaded region, I should say. The area of the shaded region, which I am going to call S. Call that region S. And that is the focus of this section, is I want to figure out, well, how could I find the area of that region for which I do not have a set formula, for which the sides that enclose that region are not straight lines. And we're going to start here. Let's try to approximate that area, and let's do it using rectangles, because rectangles seems to be the shape that the other shapes that we found the known areas for above came from. So let's approximate the area of region S, the area of S. And let's start this by using rectangles. Okay. So let's see here. I'm going to draw that figure again. Okay. So this is again my point 864. This is f of x is equal to x squared. And I want to find the area of that region that I'm going to approximate. So I'm going to say divide this up into maybe 4 rectangles, like that. So I'm taking, let's see, this is the x value 8, and I'm taking that distance from 0 to 8. This is the x value 0, and I'm dividing it into 4 parts. So this is 2, this is 4, this is 6, that's 8. So the distance from 0 to 2 is 2, distance from 2 to 4 is 2, distance from 4 to 6 is 2, and the distance from 6 to 8 is 2. Okay. Now I'm going to form rectangles. Those figures that I drew are not rectangles. I'm going to make them rectangles. I'm going to say, I'll let the height of that rectangle be whatever the y value at that point is. I'm going to let the height of that rectangle be whatever the y value at that point is. Do the same for the other 2 rectangles. Okay. So I have 4 rectangles here that I have drawn that are an estimate of that area that we are interested in. Okay. And let's see, what have I done here? I have, as mentioned, divided the area into 4 parts. I want to find the area of each of the 4 parts. So I've divided that interval 0, 8 into 4 subintervals. I'll put that in quotes, subintervals. Each of length, let's see, the distance from 0 to 8 is 8. So if I divide that into 4 pieces, each of them has a length of 2. Those subintervals are 0 to 2, 2 to 4, 4 to 6, and 6 to 8. We might call this a partition of the interval from 0 to 8. So those intervals are the bases of each rectangle. How do I find the height of each rectangle? Let's see, the height of the rectangles. Well, let's see, this point here is the point 2, 4. This point here is the point 4, 16. And this point here is the point 636. I got those using the function. Those tell me the heights of my rectangles. So it appears that the height of that leftmost rectangle, the height of the first rectangle is f of 2, which happens to be 4. I might call 2 the right endpoint of the first interval. This is the right endpoint of the interval. That first interval being down here on the bottom left, that interval from 0 to 2. The height of the second rectangle, which is this rectangle here, we said is 16. And we can get that by taking the function value at that x value 4, which is equal to 4 squared, which is 16. That happens to be the right endpoint of the second interval here. It's 4. I can find the other heights similarly. Height of the third region is f of 6, which is 36. And the height of that fourth region is f of 8, which is 60. Okay, so I have the bases of each rectangle. I have the heights of each rectangle. I can multiply the base by each height, add up all those areas, and find an estimate for the total area. So let's do that now. So the area, which maybe I'll call the area R4. I'll go ahead and tell you what that is. This is the area, the approximate area. The approximate area using 4 rectangles. R is because I'm using the right endpoint for each of the intervals that I split up 0 to 8 into, using the right endpoint. And that is equal to the base of 2 for the first rectangle times the height of 4 plus the base of 2 for the first rectangle, or the second rectangle, times the height of 16 plus the base of 2 for the third rectangle times the height of 36 plus the base of 2 for that fourth rectangle times a height of 64. If I add up all of those, I get 240 as the approximate area underneath this region from 0 to 8. All right. But we can see from our drawing that this estimate here is too big. This little area here, this area here, this area here, this area here, those are all not in this region that we desire to find the area of. They're not a part of that region S. They're outside of it. So let's see, I might call this an overestimate. And that is because what I mentioned, these parts that we counted in that area of 240 are not a part of the region S. So if I draw it like this, I would call that an overestimate. An overestimate. And as mentioned, I was taking the right endpoints of each of these intervals in question. I'll write down the intervals again. The intervals are from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. I use the right endpoints to get the height. Heights were the function values at the right endpoints of each interval. Right endpoints. So I might call this a right sum. Okay. I could perhaps repeat that process, except instead of using the right endpoints, if I use the left endpoints, let's see the estimate that I would get. Okay. So I'm going to draw that figure again. This is my curve. This is again the point 0, 8, or excuse me, 8, 64. 8, 64. And I'm estimating this region. I'm going to again split it up into 4 rectangles. But I'm going to use the left endpoint instead of the right endpoint. The intervals. These are my intervals from 0 to 2. So this is 0, 2, 4, 6, and this is 8. So my intervals are 0 to 2, 2 to 4, 4 to 6, and 6 to 8. So let's see if I use a left endpoint for the area of, or for the height of this first rectangle. And that would be what my rectangle would look like. I use a left endpoint for this rectangle. Looks like that. There's that. And there's that. So this is essentially the area in question that I'm using to approximate this complete area underneath the curve. So let's do those calculations. I can tell that just like we calculated for the previous problem, the base of each rectangle is 2. The heights, we're using the left endpoint. The height, let's see, the height of that first rectangle, the leftmost rectangle, we get by taking f of the left endpoint, 0. So I'll go ahead and note what that is. This is the left endpoint. Left endpoint of the first interval. First, similarly, the height of that second rectangle I get by taking f of 2. So the second interval has a left endpoint of 2. The height of the third rectangle has a value of f of 4, the left endpoint of the third interval. And the height of the fourth rectangle in question, that's this rightmost rectangle, is f of 6, the endpoint of this final interval. Put those into my function. I get 0, 4, 16, and 36. So I have the base of each rectangle. I have the height of each rectangle. I can write a expression for the approximate area using that breakdown. So we're going to let's let L4 instead of R4 be the sum of the areas. The sum of the rectangular areas, L4, is equal to the base of the first triangle times the height of that first rectangle, excuse me, plus the base of the second rectangle times the height of the second rectangle, plus the base of the third rectangle times the height of the third rectangle, plus the base of the fourth rectangle times the height of the fourth rectangle. If I find the value of that in my calculator, I get 112. Okay, so that is another approximation of that area under the curve, which is S. So it's this entire region here. That's what we're trying to find the value of. And you might notice that this sum that we calculated is less than that desired region. It leaves out this part here and that part there and that part there and that part there that are a part of the region S. So we might call this an underestimate. This is an underestimate. Underestimate. It was found using the left endpoints, so we might call it a left sum. Okay. It is relatively obvious that the actual area of that region S underneath the curve is greater than this left sum. So something we might say is if we let A be the area, so that's a number, area of that region S. S stands for the region itself, while A is the area of that region. Then A is obviously greater than 112, that estimated region area of the region that we found. It's also less than 240, which is the upper estimate that we calculated before. I use the term upper estimate. This also is often called the lower estimate. Lower estimate. Okay. The left sum in this case was an underestimate or a lower estimate. The right sum was an upper estimate. So this is what we got by calculating 4. This is what we got by calculating R4. And we can see that the actual area is somewhere in between these two. That is not a very good estimate, either one of them. And so you might ask, well, how could we get a better estimate? The relatively obvious answer would be, well, 4 rectangles was not a very good estimate. What if I used more rectangles? What if I split this region up into, say, 8 rectangles? And that's what we're going to try next. I think that we will do it in another video, though.